So we also have the Fermi's left-hand rule for a moving charged particle. And then in this case, the only difference is that now I don't have the direction of the currents represented by the middle finger, but we use the middle finger to represent the direction of velocity. And here, this velocity is the velocity of a positive charge. So when you have a particle that is positive, then you can just connect the direction of the velocity of this positive charge to the middle finger. If you're dealing with a negative particles, for example, electrons, then what we need to do is to pretend it is positive first and then reverse your answer at the end. Then reverse answer at the end. So this is how we do it. And the magnitude of this magnetic force is given by QVB sine theta. QVB sine theta. F is the magnetic force in Newton. Charge Q, here we only use the magnitude of the charge, so therefore you will not have a negative number for the force to confuse yourself. V is the velocity. Again, velocity technically is a vector, so we are actually, when we say velocity, we are just using the magnitude. But usually okay. Most students will not certainly put a negative velocity in it, but they will have a chance to put a negative charge into there. So, yeah. And then B will be the magnetic field strength in Tesla. And the most complicated one will be the theta. Theta is the angle between B and V. All the non-trivial physics about the magnetic force on a charged particle is in the sine theta. So you can put an example that we look at some extreme case. How can we do an extreme case? We could we can look at this. Let me think about it. Let me say I have a region of magnetic field. And then in this region of magnetic field, you have a uniform field which is pointing into the page. So uniform B field is into the page. So I just denote it as circle with a cross, circle with a cross, circle with a cross, circle with a cross. And I have 4 particles. They are not moving. They're not moving in the circle. I just try to put it like this. So this charge Q, which is positive. And this positive charge is moving in the direction this way, velocity. And then I have another particles which is negative, and then its velocity is going this way. And I have another particles which is positive, but it is at rest. Okay, like this first. Then we can talk about the force exerted on the charged particles. You can use the Fermi-Stephan rule. For example, for this case, FBV. So the velocity is this way, and then the magnetic field is the velocity this way. So the magnetic field is going into the page. So, and this is a positive particle, so the force is pointing out. So for the first particles, then we use the Fermi-Stephan rule, and then we can deduce that the force is going up. For the second case, it's a negative particle, but I can pretend that it is a positive particle. So we just do the same as before, velocity going this way, momentum, magnetic field going into the page, so the force is going up. The force should be going up, but it is negatively charged. Therefore, we should reverse the answer, so the force becomes going down. Okay. And then, finally, this one has a positive charge in a magnetic field, but it is at rest. So therefore, according to this equation, because V is 0, therefore, although you have charge, although you are in a magnetic field, but there will be no magnetic force exerted on it. So therefore, this last scenario will have no force. Another example would be you have a magnetic field which is pointing to the right-hand side. In other words, for example, you have a north pole here, and then you have a south pole here. Please remember the magnetic field is pointing from north to south, not the other way around. And then this time, I have a particle going these. Now there are 4 different particles. Not in a circle. Let me break it this way. Therefore, you do not take it as. And then they have a charge of this is a positive, negative, positive. Do I do that? Maybe positive, negative. Now, then in this case, what is the magnetic force?
0 for the first one.
0 for the first one, because the angle between the velocity and B field is 0. The B field is pointing to the right. This is also pointing to the right. Therefore, the angle theta is 0. So sine 0 is 0. So the same thing is true. It does not matter the charge is positive or negative. The direction of velocity is parallel to the direction of the magnetic field. So therefore, you will still have sine 0. But these two, they still have the force.
Into the paper.
This one first, maybe
Yeah,
into the paper.
then out. This is negative.
Yes. Okay. The velocity is going up. The magnetic field is pointing to the right, so the magnetic force is going into the paper. Well, the same thing applies here, or this, but the charge is negative, so we have the force to be reversed. So therefore, you will have a force pointing out of the paper. So here there will be a force out of the paper, and then it will be a force into a paper, and then here there will be no force. What happened to this? No force. Now, this is a very interesting thing, because it implies that when you suppose you imagine you are a charged particles and then you enter a magnetic field, then you may expect that, oh, I should experience a magnetic force, but this is actually not true. If you are moving, but you are moving along the direction of the magnetic field lines, then we will have the sine theta in this equation that turn off the magnetic force. Okay. So here, because it's sine 0 equals to 0. The same thing here, sine 0 equals 0. Okay, now, then the next thing that it can be asked will be about the magnetic force on charged particles, and then we look at the motion of the charged particle as a circular motion. So what is this here is a so-called motion, the circular motion of charged particles in a magnetic field. This part here essentially is to say that because in general, you can consider, let's say you have the velocity of a particles going like this is a positive charge, and then using the Fermi-Safran rule, let's say you are in the region of, let's say, magnetic field going into the page. Then using the Fermi-Safran rule, then you will find that the force is pointing to the left. And this is a very important feature, is that because of your Fermi-Safran rule, you find out that the force and the direction of the velocity will always be perpendicular to each other. So it is very common that, it's very general, that the magnetic force is perpendicular to velocity. And this implies that magnetic force can act as a centripetal force. So therefore, the motion of a charged particles in a magnetic field will be circular if there is a magnetic force exerted on it. So in other words, you can combine the magnetic force formula, which is QVB, and then we take sine theta equals to 1, theta equals 90 degrees, and then make it equals to the centripetal force, which is mv squared over r. The magnetic force equals to the centripetal force. This is actually not completely new. We did the same in the topic of gravitation. In gravitation, we say that the gravitational force acts as the centripetal force. For the case of gravitational force, we have G mm over r square, and then we equate this to mv square over r. So it's not new. We actually did similar before. We equate these particular types of force as a centripetal force. So after this, then we have QEB equals to mv squared over r. Then one important result will be to solve for radius r. And using some simplification, then we have v mv squared over qv b. Therefore, I can cancel one of the v. And this is the answer. That the radius is equals to m times v divided by qb. And sometimes we may write this mv as the momentum, because mv is just momentum. So this is momentum over qb. This is usually the end result you could derive, because you need to remember that this equation is not given, this equation is not given. So being able to recall this equation and then derive this result is already quite non-trivial. Another result that will also appear will be, we are not interested in r, but we are interested in the period of the circular motion. Because you know the electron is orbiting in the, is undergoing a circular motion in the magnetic field, then we can talk about how fast does it move? How long does it take to complete one circle? Then this goes to finding the period t. But how do we find the period t? In the case of charged particles in the B field, similarly, how do we find the period t in the case of gravitation? What t equals to? There is no t at all. There's no t at all in this equation. So that means I need to find t in terms of some variables in this equation. How is the t related to r? How is the t related to v?
So is it like, was it t equals
2 pi over r?
2 pi over something?
2 pi over something.
Yeah.
Or that's 2 pi over omega, angular speed or angular velocity. But no, something seems here, in fact. You are in a circular motion. What t stand for? T is the time taken to complete one circle. And then let's suppose it is moving at a speed of v, and then the radius is r. What is the distance traveled in one cycle? 2 pi r. So t is just 2 pi r over what? What's this? This is just equal to time equals to distance over over velocity. Over velocity or over speed. So it's just 2 pi r over v. This is the beginning, the first step, that how you relate the time period t, or how do you find the period t? Because the period t is something just like come from nothing, because most calculation here, let's say the force QAB or the GMM over R square or the MV square over R, there's no T in it. But T must be related to this. Well, the relation between T and the V and R is, it turns out that it's just very trivial, 2 pi R over V. Distance traveled over time, distance traveled over speed will be equals to the time taken. So after doing this, then we can plug that R into the formula. So we have 2 pi over V times R, and R is equal to MV over QB. So we can cancel V. Therefore, we have the period T equals to 2 pi M over QB. So this is another famous result. Or at least the result that we can obtain from this. QEB equals to MV squared over R. Okay. So this is about everything about the force exerted on a charged particle. You need to learn about the direction, you need to learn about the magnitude, the sine theta is very important. And then after that, so this part on the top will be talk about the direction and the magnitude of the force. But okay, then afterwards, you want to study how does it move. Well, the motion of the particle in a magnetic field will be a circular motion. So you want to study how does it move, how big is the radius, or how fast or how long does it take to complete one cycle, then you have to obtain those information using MV squared over R equals to QAB. Yeah. Okay, now, so after this, then we talk about the induced EMF and induced current. Now, to talk about induced current, induced EMF, I think I should start from magnetic flux linkage. So we got something, the magnetic flux linkage. Magnetic flux linkage is in the unit of Weber, WB. The formula of it is just N, B, A, cosine theta. N is, this part is actually electromagnetic induction. Let me put back the title. The language we use in the electromagnetic induction is the so-called magnetic flux linkage, which is N. N is the number of turns in a coil. B is the magnetic field strength. Or in this topic, we will call it magnetic flux density. Is it the same? The only tricky part is T will be the unit we use for the magnetic field strength, while when you call B as a magnetic flux density, you usually use Weber meters minus 2. A is the area of the coil, and then the theta here is the angle between B and the normal of A. Compared to the sine theta we did before, this cosine theta relatively is not that test frequency. But anyway, let's demonstrate roughly what this is about. Is that you have a loop. Let's say you have a loop and then you have got a few terms, 1, 2, 3, 4. N equals to 4. And then you have the magnetic field that is going along the loop. Like this. This is the B field. Then the normal of the area is this. So the angle between the normal of A and the B field will be so-called theta. So therefore from this you see that what if theta is 0 and what if theta is 90 degrees? If theta is 0, that would be so nice because the loop is horizontal and then the field lines are all vertical, so the B field is really going into the loop. But if the theta is 90 degrees, then that means the loop is horizontal, but the B field is like this. That means the B field does not go through the loop. So in this sense, it means that you don't have magnetic flux linkage. So from this, if theta is equals to 0, then you have the maximum linkage. So you just have to use B and BA because you really just enclosing the linkage. Well, however, if you have the theta equals to 90 degrees, then you have minimum, or in fact, we should say 0 linkage. You can think about that the coil cannot link to the field lines. It's even not going through it. So in this intuitive understanding is quite important if you want to fully understand the magnetic flux linkage. So after this, then we have the language now. Then we can just use the so-called the Faraday's law. The Faraday's law of electromagnetic induction is to say that the EMF induced is equal to the negative of the magnetic flux linkage. Like this. So this EMF is this E is the EMF induced. This whole thing here is the magnetic flux linkage, or this N phi here is the magnetic flux linkage, the one defined above. Although it's written as N phi, but it's just nothing as NBA cosine theta. It's in the unit of Weber. But more importantly is this whole thing. We're not doing differentiation, but we need to use this notation because we want you to take it as the rate of change of the flux linkage. We're not doing integration or differentiation here. So the rate of change is not to be phi using differentiation. But we do need you to know because we can take rate of change of flux linkage as the slope of the N phi versus time graph. So therefore, the Faraday's law, when you really use it, you are using it as a graph, as a way to analyze a graph. That you are given a graph, and then you differentiate, Then what you need to do is to find the slope of the graph, then you can find the EMF. So So if I cannot do this. So one application will be you have the region of magnetic field, and you have a coil, this coil, you have a coil, and this coil is moving across the B field. So therefore, the magnetic flux linkage as a function of time will be like, at first there's no flux linkage because there's no B field, because B field is only here. At first it is not in the field yet, there's no linkage, but afterwards it gets into it. So the flux linkage increases. Within the field, the flux linkage stay unchanged. And afterwards it's leave. So it go out like this. So the Faraday's law tells you that let's look at the EMF. The EMF is just the negative of the gradient of this graph. So E equals to the negative of the gradient of this graph, or the slope of this graph. So therefore, the EMF can be found. For example, for this part, you got a positive gradient. So the EMF will be negative. For this part, you have a zero gradient. So the EMF is 0. For this part, you have a negative gradient. So the EMF is positive. So therefore, there will only be EMF induced whenever there is a change in magnetic flux linkage. But the EMF induced will be opposite direction between entering and leaving the field. This opposite direction of the current of the EMF will give me the current as well, because EMF induced means you have current induced, which is actually not difficult to understand, because I equals to V over R. So V here becomes the EMF. It will be just like this. If you have a finite resistance, then you will have a current induced. Of course, if you have the resistance to be infinitely big, for example, let's say I'm very tricky, I have a ring, but I cut a hole. Then in this case, yes, you have EMF induced, but you will not have currents to flow, because in this case, the resistance will be infinitely big. Even you have EMF induced, for example, you're just holding a cell, you hold a dry cell, but the resistance of my hand is infinitely big, so there will be no current. So, of course, there are more details we can talk about for the magnetic electromagnetic induction, but the principle of the electromagnetic induction is about this. Oh, we finish here. 2 hours.